Hi and welcome back to another LeetCode video. We're looking at an easy problem today. LeetCode 2273, find resultant array after removing anagrams. I'm just going to read through the description and then tell you what my approach will be to solve this, including space and time complexity analysis. Kind of the same way you would do it in an interview when you analyze a problem, check your assumptions, and then come up with an implementation idea. Runtime and space complexity before you write the first line of code. So let's do this. So we are given a zero index array of words, called words, where the word at position I consists of lowercase English letters only, I suppose. In one operation, we can select any index I such that I is larger than 0 but smaller than the length of the words array, and where words at the previous position and the word at the current position I are anagrams. If that is the case, then we delete the word at position I from the words array. We should keep performing this operation as long as we can, and yeah, as long as we can. And after that, we should return words after performing all operations. It can be shown that selecting the indices for each operation in any arbitrary order will lead to the same result. Right. And as a reminder, an anagram is a word or phrase formed by rearranging the letters of a different word or phrase using all of the original letters exactly once. For example, DACB is an anagram of ABDC. Okay, so let's look at the constraints, because we want to know how long can the words array be and how long can the words be. And there's the answer. So the length of the words array is at least 1. For the sake of complexity analysis, we're going to ignore the fact that it has an upper bound. That is only interesting for LeetCode so that it can run our code. And each individual word has at least 1 character, and at most 10. We're also going to pretend that we don't know how long these words can be for our analysis. And of course, every word consists of lowercase English letters. Nice. So yes, so how can we approach this? Well, I think the first example could give us a good hint. So here we have 5 words. We can see that the first 3 words are anagrams of each other because they contain exactly the same letters, just in different order. And that means in our result array, we're only going to pick the first one of the sequence of anagrams. And then when we run into the next anagram, which is not an anagram of the previous word, we start the same process. So we will only keep the first word. And yeah, and we can only, we have to delete an anagram when we have 2 words that follow each other, that are anagrams of each other. Okay, so here's another example. Okay, in this case, all words are different, so the output is going to be the same as the input because we can't delete any words. Right, so how can we approach this? Well, I'm thinking that we could just do exactly what we've just observed. We just iterate through the array from left to right. And when we see that the previous word is an anagram of our current word, we're just going to skip over it and we're going to ignore it. And that is the approach that we're going to use. Now the question is, how do we determine if 2 words are anagrams of each other? For that, we would have to find a way of making them easily comparable. And typically what you can do is you can just sort the letters in the word, and once you've sorted them in each of the words, then you can do a direct string comparison between them. They're the same, that means they have the same number of letters, and they have the same frequency of each letter. So we're definitely going to need a little helper function that calculates us maybe, well, a normalized version of the word. And I think we can do that with bucket sort, because we know that, or a counting sort maybe, because we know that every word, that the letters are between A and Z. So that is a fixed number that is bounded. So what we'll do is we'll iterate over our word array, a words array from position 1. And now what we do next is, well, we have to compare, obviously, if the current word is an anagram of the previous word, right? So we will have to have a little helper function. And well, how should we call this? Maybe we call this get signature. So we will just say that the signature of a word is pretty much all the letters of the word in sorted order. But we're not going to do it in n-log n time, right? Which, depending on the length of the word, can, well, take n-log n time. We're going to do it in linear time. So we're going to iterate over all of the characters in the word. And we're going to, well, we're going to have a little histogram or a frequency array that contains the counts for every letter. And we know we only have lowercase English letters, so we'll only have 26 possible letters. And then what we'll do is we just increase the counter at the at the position of the word. So what we're doing here is we are mapping the ASCII code of the letter to the range between 0 and 26. And having offsets or something doesn't matter. So our letter A might not be at position 0, but we don't matter. We just care about the shape of the histogram. Right, and in the end, what we need to do is, well, we need to, I suppose, return the histogram. What we can do is we could turn it back into an array. We could turn it into a tuple. And I'm just going to turn it into a string that we can construct in a constant time. And the way to do that is we'll just iterate over the histogram for I in inch. Length of the histogram, I could just put 26 if I wanted to. It's the same thing. Our result is going to be, well, I'm going to use an array to store the intermediate parts of it. And I'm just going to join them into a string. So, well, how do I do that? Well, what I do is append the count. So the count is, well, the histogram at position I. And maybe well, I just need the count, to be honest. I just do count. And, but I'm also going to attach like maybe a comma. So what this will be a string that contains the counts of the letters, 3, 0, whatever, however many times. So that's going to be the signature of a word that we get. And the signatures, because we are, well, we're essentially using counting sort, and because we are generating the signature in descending order of the characters, means we're actually getting a sort of like a signature that is based on the sorted characters and the counts. So that will make sure that two strings have the same signature when they're anagrams of each. Right, so what we'll do now here is we will say the previous word is words at position I -1, and the current one is words at position I. And now we just need to compare their signatures. What we'll do is, if signature of the previous one is the same as the signature of the current one, well, we're going to ignore it. We're not going to do anything. But if they're different, that means we're going to have to add the current signature to our result list. So, and we'll say result.append current. And of course, we need to keep track what the previous one was. And because we're starting in index 0, that means we have to put the first word into our result dictionary. It's guaranteed the first word will always end up in it. Only subsequent anagrams will be skipped. And then in the end, we just return the result array. So let's see. And in terms of space and time complexity, well, we said that we will have n is the length of words and m is length of long word. Now for second time, and so, well, we're iterating over all of the words. So it's definitely n times something something. Now, to compute the signature, we need to iterate over all of the characters of each word. So it will definitely be O of n times m time. And in terms of space, well, in the worst case, we're storing all of the words again, and we will have done all of our comparisons. So it's the same space complex. And let's run this now to see if this implementation works. Not tried it before. Word is not defined, so W, not a word that has in here. And so the test case pass here. Now I'm just going to submit this to see if it passes all of the tests. Right, so that works. Now, what we can also do is we can probably reuse our words array, because we technically speaking, we don't have to keep track of, or we don't have to construct a new results array. We could just reuse words, couldn't we? So what I would do is, I would, in this case, I would have maybe, let's say we'd have a left pointer, and we keep that at 0. And then we just iterate with the right pointer over our array. We can keep track of well, we should also probably keep track of the previous signature, right? And that one will be, well, how should we best do this? Well, we're going to iterate over all of our indices, and whenever we find that the signatures are not the same, when they're not the same, well, that means I'm going to increment our left, and I'm going to write the current one into the left array position. Essentially what we're doing is we are skipping over the words here. Our left will be at index 1. We're skipping over these anagrams of our first found word. And when we find the next word that is not an anagram of the previous one, we write this as position, the index, and increment our left of the index that is pointed to by the left pointer. And then we increment this. And then in the end, we can just truncate the array and remove however many cells we didn't need to keep track of. In the array, I mean. So let's see if the signature, so the previous signature is, well, our current word. We start with words 1, right? Words, first word. Previous signature is that's what we have. We start with our left index pointing at 1. And now we're starting with the right at 1 as well. Now we're checking if the previous signature is not the same as the current signature. Let's determine what that is. If they're unequal, well, that means we're going to write our current word, which is at index I. We're going to write that into our words array at position left, and then we do the increment, right? So left always points to the next position where we would write the next word to that is not an anagram of a previous word. Now, of course, we have to determine a previous signature. We just keep track of it. So that way we avoid recomputing the previous signature. So current is words at 0, and we can delete that because we're never going to modify the word at index 0 of our words array. And let me think through this real quick. So we say that the first word is set at index 0, and that means we increment left by 1. Actually, we could make this even simpler. Previous signature, we're just going to say it's the empty string, and we say left is 0, and we start from index 0 as well. So what will happen now is we get the current word. It will have a different signature than the previous signature. So we write word into the left position, increment the left by 1, which is exactly the same behavior. And I think that should work out for us. So let's run this. And let's see. Current is words at position I. That's of course wrong. So we have to pick position right, not left, not I. And of course, we're not returning the result anymore. We're returning words. Now, we also, and this is something that I forgot, have to remove the elements from the end of words. And left is now pointing at the position we would insert the next word to, or the last word that we need to remove. So while the length of words is larger than left, we're going to remove the last word from words. So, okay, so this test case, the test case is pass. Let's submit this now and see if all, and they do, right? So that is another approach. It does not reduce our time complexity, but it reuses our space complexity. Of course, we're not going to have to build an array of all of the words. However, we still have to construct the signatures, which are length m, not multiplied by the total of words. So that's a slight improvement. And that is only possible because we're now reusing the words array to return the results instead of creating a new